Welcome back to Zero Dark Emissions. So last time I said this next episode would show the installation of the motors and gearboxes, but I have a bit of a lead time for this equipment, so while I'm waiting, I'm going to skip ahead to working on the low voltage system. I was going to handle this next anyway, after the motors, before moving to the rest of the high voltage system, so that I would be able to connect the EV components to the low voltage system where necessary. But since I have some time, and since there is nothing preventing this work from moving forward, I'll take it now. I'll warn you in advance that there is a lot to cover, so I'll be doing a lot of talking in this one, and we'll have a lot of screen time. So first I remove the existing wiring harnesses from the vehicle, and there are basically 4 harnesses not including the ground harness. These are the engine harness. This includes things like the glow plug connectors and other engine and transmission connections, and this harness has nothing that we need. This entire harness will basically be trashed, except that I may salvage the connectors or some of the wire for use on the new harness. Next is the STE ICE harness, and this is where the big diagnostics connection ties into, and this also has nothing that we need. Then we have the hood wiring harness, and this one will not only be reused, but will essentially be completely left as is. Nothing to add or remove, except that I will remove the existing loom and put a new loom on it just to clean it up, and also replace some of the connectors that are worn. And finally, we have the body wiring harness shown laid out below the vehicle, which is the most complicated in that there is a bunch of stuff that we will want to reuse and or modify, as well as a bunch of stuff that we will want to remove, and also new stuff that we'll need to add. We will remove all looms so that we can modify as needed. To get a better handle on this, I'll show you the wiring diagram that I put together, but first starting with the wiring diagram from the technical manual that I started with, then modifying it to add and remove various items as needed. By the way, I see a lot of people using a butchered and incomplete wiring diagram that they find online, but the complete wiring diagram for the M998, as well as some other models, can be found at the back of Volume 3 of the Unit Maintenance Technical Manual. Here you can see the complete stock wiring diagram with a bunch of my highlights showing things to remain versus things to be removed, and also tracing out certain power and ground circuits. I then edited this to wipe out all of the stuff to be removed to get a cleaner look. I then took this and created my own wiring diagram in CAD, where I could more clearly show the portions of the wiring harness to remain, as well as show added circuits for the new setup along with notes on modifying this harness. You will see some different colors, which are just my way of keeping track of items that I have acquired and installed versus items that I still need to acquire. But the main thing to note is that all of the circuits shown dashed are items that are existing to remain, and all circuits shown as solid lines are new. Also, red lines are positive and black lines are ground. Here you can see the hood harness, and as mentioned, it is basically left intact with no modifications, except for some minor things like replacing worn connector plugs as mentioned. Here you can see the Cannon plug that connects the hood harness to the body harness, and this is being left intact. Here you can see the body harness, and as mentioned, this is being substantially modified for the new setup. Up above here are the new EV wiring harnesses, which I will not cover right now, but we'll cover these in more detail in a future episode. The main focus of this episode is the modifications to the body harness. As you can see, some of this gets a bit complicated, so I will go through the more complicated items, but starting at the beginning with the battery box and main distribution panel and work out from there. The battery, which will be a single 12-volt battery for a 12-volt system, will remain in the general current location under the passenger seat, and the main distribution panel will also be located there. I'll be modifying this box to eliminate the existing partition that is there and putting in a new partition in the opposite direction that will configure better for my setup. I'll come back to that later. By the way, the reason that I'm going with the 12-volt system is basically to save some space and the cost of the extra battery. The advantage of a 24-volt system is that you pull half the amps to perform the same work as on a 12-volt system, which means that the wiring can be smaller gauge with 24-volt versus 12-volt. But in conjunction with going from 24-volt to 12-volt, I am also drastically decreasing the amperage on all of the existing lighting by going to LED, which is what most of the existing stuff to remain is, so I am safe with the existing wiring. I am keeping some 24-volt circuits, which I will get to later. For most of the new wiring, I'll be using the same 14-gauge Prestolite wiring as what the Humvee uses for the most part, The existing does also have some 16 gauge, which I will not be using. I will also be using some larger wire where needed. I have some 10 gauge, some 12 gauge, as well as 4 gauge at the batteries. The way that I'm going to set this up is to have my 12 volt positive coming off the battery extend to a 200 amp breaker on my main panel. There will be fuses downstream of this, but I like the main breaker as an easy way to cut all power when working on the vehicle. Coming off the main breaker will be 2 lines, one that extends to a constant power fuse block for power that is always active even when the key switch is not turned on, and to a keyed power fuse block, power that is only active when the key switch is turned on. One to the constant power is pretty simple, just a direct line from the breaker to the fuse block. This fuse block would handle circuits for the key switch that flips the relay to provide power to the keyed power fuse block, as well as the headlights and other exterior lights, always operable, typical of most vehicles, and the coolant pumps and radiator fan, so that these cooling related items can run when needed during charging or are still hot after turning the vehicle off. There are also some EV related items on this fuse block which I will cover in a future episode. This fuse block is rated for 100 amps, but I am not introducing a separate 100 amp fuse ahead of this block, since I should not be pulling 100 amps from this block. The line going to the keyed power will pass through a 120 amp fuse before going to the 120 amp relay that will turn this panel on from the key switch. This relay then goes to 3 fuse blocks, a 100 amp fuse block similar to the constant power fuse block to handle most of the keyed powered circuits, as well as 2 individual 40 amp fuse blocks for the power steering and power brakes. These are necessary since we need 40 amp circuits for these 2 items, and the main 100 amp fuse block can only have a maximum of 30 amps on an individual circuit, and would also probably max out the 100 amp limit on the overall fuse block. Note that I'm using fuse blocks without a grounding bus, and I'm using a separate single grounding bus for all circuits. This just gives me a little more flexibility when physically arranging the components on the board. One final item in this main distribution area is a 12 volt to 24 volt transformer. Although I am generally converting from the stock 24 volt system to a 12 volt system, there are a few stock items that I am keeping that will require 24 volts. These are the windshield wiper motor and associated windshield washer motor, as well as the cabin fan. So one of my circuits coming off the keyed power fuse block will run through this transformer and serve those items. Okay, so now that we've looked at the diagram, here is a look at how this will be physically laid out. Here you can see the passenger seat footprint, and within that footprint there is the battery, with power going under the panel to the main breaker, and then coming off to the constant power block, and to the keyed power blocks through the 120 amp fuse and relay. The transformer is located here, and the ground bus is located here, with the main ground coming back to the negative on the battery under the panel, connecting to the body to ground the body along the way. And here you can see the new main partition that will allow for a small storage area in the leftover area here. Originally I wanted this panel to be oriented vertically, but orienting it horizontally gives me a bigger footprint to fit all of these items. The actual board is made out of 5/16 ABS plastic sheet, thermoformed at the corners to give it rigidity and space for wires below. The idea will be to locate this at the bottom of the passenger seat box, and then have another identical one sit on top of this to act as a protective cover, and also allow for some storage above it. The whole sandwich will be held in place on 2 existing sides within the box footprint, and then by 2 added partitions on the other 2 sides. I will also have a steel bolt coming up through the center of the assembly that will go through a small section of plastic pipe and cinch down with a nut. This will provide additional support at the center of the board so that it doesn't deflect and keep the whole assembly tied down. You can see that I have already laid out the components and drilled all of the bolt holes and holes for the wires to pass through, so we can go ahead and start putting it all together. here's the completed board, ready for all the various circuits to be routed to the fuse blocks, as well as the cover over the top. Back to the wiring diagram now. Extending off this main distribution panel, we first have our run switch circuit, which extends from the panel to the key switch. That delivers power to the relay and back to the ground bus. This relay, when closed, then provides power to the key power blocks. Also on this constant power block are the circuits for the coolant pumps and radiator fan, which are pretty simple, as well as some other circuits that relate to the EV setup, which we will cover later. Finally, there is a circuit for the headlights, taillights, and marker lights, and this one gets a bit hairy. The complicating factor for the lights is that we will be replacing the stock Humvee light switch for something that is a bit more logical and comfortable for our normal non-military use. I'm basically trying to achieve a few basic modifications to the existing setup. First, I want what the stock setup calls stop light, meaning that basic stuff like the brake lights and turn signals work, to be on without having to proactively turn this on to the stop light position. I would still have a blackout option on the switch, which would turn on the blackout lights and disable the headlights, brake lights, and marker lights, but this would require proactively turning to that position. The other thing is that I will be eliminating the floor switch for high beams and placing this up on the dash along with the main headlight switch. Here's the switch that I will be using, which is just a standard vehicle switch. The off position is straight up, and then you would switch it back one position for blackout mode. Moving forward from the off position, you have parking lights and then the headlights. The high beams will be activated by a separate push button, which will also light up when pushed to provide an indication that the high beams are on. The complicated part of this is determining how all of the various wires that come into the existing switch interface with the turn signal, which we will be keeping, and then go out to all of the various points. And for this, we will go back to the stock wiring diagram. Here you can see the light switch, and here is the turn signal. This circuit labeled as 15 shown in green is the power coming from the smart box into the switch. This is a short section of wire between the smart box and the switch, which are physically located pretty close to each other, and we will eliminate this wire completely in favor of a new power circuit from our constant power panel to the new switch. Next, you can see this circuit labeled as 75A, one of the wires shown in dark blue. This provides power to the brake light switch, and when the vehicle is either in stop light or blackout mode, also relays this power when the brake pedal is depressed through the turn signal via circuit 75B into the switch, and then to 22A for stop light mode to the turn signal shown in red. For our setup, we will want this to be powered all of the time unless we place into blackout. Also shown in dark blue are circuits 467B and 21A. These are circuits that relate to the turn signals and are also only active when the vehicle is in stoplight mode, but we will also want these active all the time unless in blackout. One other thing to note in this area is the flasher relay, and this will be a new 12-volt flasher relay, replacing the existing 24-volt flasher relay. So back to our wiring diagram, here again is our power in from the main distribution. This power is then delivered to our new headlight switch. After testing the 10 pins on this switch, I was able to determine the pin for incoming power, which is pin 7, the pin for ground for the internal light, which is pin 1, as well as the pins that control the parking lights, pin 5, and the headlights, pin 10, as well as what I will be using for the blackout function, pin 4. So taking them one by one, the blackout function coming off of pin 4 routes to circuits 19A and 20A. 19A is for the main blackout light at the front, and 20A is for the small blackout marker lights at the front as well as the small blackout tail lights at the rear. Also, this pin controls 4 relays which utilize normally closed contacts. These relays normally deliver power to the front and rear turn signals, but when in blackout mode, these relays open to prevent these lights from coming on. The second position on the switch is for off, and this does not provide any outgoing power. There is actually a pin on the switch to provide an outgoing signal in this position, which is pin 9, but we will not use that. Third position on the switch is for the parking lights using pin 5, which controls a relay that provides power to circuit 21A, which routes power to the front and rear marker lights, as well as to interior display lights at the shifter box, and also back to the switch to light up the internal light in the switch. This relay is provided for a couple of reasons. First, it provides power directly from the battery to the marker lights without running through the switch. And secondly, this relay, along with the relays for the headlights and high beams, allows the parking lights to be on during all of these functions, providing a separation so that power is not backfed through the parking lights or headlights, depending on which function is selected. The fourth position is for the headlights using pin 10, which controls a relay to provide direct power through the high beam switch. When the high beam switch is not pushed in, power is delivered through the normally closed output to circuit 18, as well as to the parking light functions via the relay. When the high beam button is pushed, the button lights up and provides power through the normally open contact to circuit 17, also running power to the parking light functions. Note also that a connection is made between cut line 75A going to the brake pedal switch, cut line 467B going into the turn signal, and the power coming from the fuse block. This allows the brakes and turn signals to work in all switch modes except for blackout when the relays break the circuits for the front and rear marker lights and turn signals. One other item to note here is that circuit 75B from the brake pedal switch needs to be connected to 22A from the turn signal switch. These are cut lines from the original Humvee switch that were operated via the stoplight mode, but that I want to be permanently connected. These lines are connected to 23A, which go to the blackout brake lights, and I have also added a takeoff that will go to the inverter motor controllers to tell them that the vehicle is braking. And here's what the completed switch assembly looks like. The switch will be mounted in the same place as the existing switch, but with a new plate over the dash that will clean this up and just give me the holes that I want in the new setup, and the relays will be mounted below the dash. Here you can see the switch turn to blackout with the blackout light and small marker lights illuminated. Back to off, now to parking lights, and now to headlights. Now with the high beam button depressed, and here you can see the turn signals and hazard functions working without any need to turn to a stoplight function as with the old switch. Note that when in blackout, the main markers and turn signals do not operate. Here it is from the rear with blackout markers, main markers, turn signals, hazards, added license plate light, and brake lights all operating as desired. The next thing I'm going to cover, which is also relatively complex, is the switches for the shifters. This is for the rotary switch that will operate park, drive, and reverse, and the push button that operates four-wheel drive. I was originally going to place these switches at the original shifter box location, but I decided to place on the vertical section of the firewall below and to the right of the steering column in the same location where I will place the starter switch. I like this location better since it is more out of the way and less susceptible to damage on the horizontal surface at the main deck. I'll start by talking about the simpler of the two switches, which is the four-wheel drive switch. I was originally going to utilize a rotary switch which would toggle between a two-wheel drive and four-wheel drive position, but I decided to use a push button with one normally open output and one normally closed output. This just takes power into the switch, and in the two-wheel drive position, when the button is not depressed, provides power through the normally closed output to a double pole double throw relay, which provides power to an actuator that would shift the locking collar at the front drive disconnect to the off position. When pressing the button, the normally open output provides power to the opposite side of the double pole double throw relay, reversing the polarity to this actuator to shift the locking collar to the on position. This position also delivers power to the front contactors, turn the inverters and motors on at the front motor, and also turns the indicator light on at the button. Note that the contactors for the rear motors are turned on when the key switch is turned on and would stay on when in the four-wheel drive position, as these come directly off of the keyed power block. The park drive reverse switch is a bit more complicated. This is a 3-pole, 3-throw switch, and you can see the first position is the park position, And this uses the first pole to go to a double pole, double throw relay, same type as the one as we were using on the 4-wheel drive switch, which controls the actuator at the park lock at the rear gearbox so that it is in the locked or parked position. The second and third poles of the switch are not used at this position. The second position is for drive and just uses the first 2 poles. The first pole goes to the other side of the double pole, double throw relay in order to control the park lock actuator so that it is unlocked, and the second pole goes to the inverter controllers to tell them to operate the motors in forward. The third position is for reverse, and this uses all 3 poles of the switch. First goes to the double pole, double throw relay, as with drive, to control the park lock actuator, also unlocking it as with drive. The second pole goes to a circuit to tell the inverter motor controllers that tells them to operate the motors in reverse. And the third position delivers power to the reverse lights and also an added rear camera. And fun fact here, my wiring harness had the reverse light circuits even though my M998 does not have reverse lights. So that was some new wiring that I was planning to add that was not needed. By the way, the reason that I am placing reverse after drive on the switch is so that the reverse lights and camera do not temporarily come on while passing the reverse position to go into drive. And here's what the completed assembly looks like. One other little thing that I'll cover is my labeling for the circuits. For the existing circuits to remain, I'm keeping the existing stock circuit numbers as well as the metal tags at the wiring. In some cases where I'm cutting the end of an existing line with the metal tag, I'm removing the metal tag and reinstalling it at the new cut end. For my new circuits, I am labeling these with an X prefix for positive and a Y prefix for ground to differentiate these as new circuits versus existing circuits. I am physically labeling these using a label maker that labels heat shrink tubing that can shrink over the end of the wires. There's obviously a lot of other smaller things that needed to be handled, such as splicing in the license plate light off the same circuit as the rear driver's side marker light, and just a lot of existing wire removal and new wire added, but just covering the bigger stuff for now. So those are the basics as well as the more complicated pieces of the system. There's still more to do with the low voltage system, but we will handle this later as we go. So next time we should have our equipment here and we'll go on to the motors, inverters, and gearboxes. See you next time.